Previously, we covered the core foundations. Now in part 3, we tackle Earth, interior and magnetosphere. In the previous episode, we looked at Earth's atmosphere, the thin shell of gas that makes life possible at the surface. But beneath that surface lies something just as remarkable and far less understood. The question this episode asks is simple. What's actually going on inside Earth? And why does it matter for everything living on it? Most of us think of Earth as a solid ball of rock. Stand on the ground, and it certainly feels that way. But the planet beneath your feet is layered, dynamic, and in places genuinely molten. The processes running deep inside reach all the way out into space, generating a magnetic field that has been quietly shielding life on this planet for billions of years. That field isn't permanent. It wanders, weakens, and has flipped entirely hundreds of times in Earth's history. How that happens, and what it would mean if it happened again, is one of the more interesting open questions in planetary science. We'll come back to that. First, let's go inside. Earth is the largest of the 4 rocky inner planets, with a mean radius of about 6,370 kilometers. Its mass is roughly 6 times 10 to the power of 24 kilograms, a number too large to mean much on its own. But what matters is the density it implies. Earth averages about 5.5 grams per cubic centimeter. Surface rocks, you can pick up way around 2.7 to 3. That discrepancy tells you something dense must be lurking deeper down. We can't drill to Earth's core. The deepest borehole ever completed, the Kola, super deep borehole in Russia, finished in 1994 after more than 20 years of drilling, reached just 12 kilometers. Earth's radius is over 6,000, so nearly everything we know about the interior comes from seismology, the study of how earthquake waves travel through the planet. Different wave types behave differently, depending on the material they pass through. Some are blocked entirely by liquid, by mapping where waves slow down, bend, or disappear. After major earthquakes, geophysicists have built up a detailed picture of what's down there. 4 layers, broadly. The crust is the outermost, thin, brittle, relatively cool. Continental crust averages around 35 kilometers thick. Oceanic crust is thinner, 5 to 10 kilometers. In planetary terms, it's like the skin on an apple. Below that is the mantle, making up about 84% of Earth's volume and extending to a depth of roughly 2,900 kilometers. It's not liquid, it's solid rock. But over millions of years, it behaves more like an extremely viscous fluid, flowing slowly and carrying heat upward from depth. That's what drives plate tectonics, which we'll look at more closely next episode. Beneath the mantle sits the outer core, between about 2,900 and 5,150 kilometers down. This layer is liquid, molten iron and nickel, with smaller amounts of lighter elements such as sulfur or oxygen. Temperatures here reach somewhere between 4,000 and 5,000 degrees Celsius. At the very center is the inner core, a solid ball of iron and nickel roughly 1,200 kilometers in radius. Despite being the hottest part of the planet, somewhere around 5,000 to 6,000 degrees Celsius, the pressure there is extreme enough to keep it solid. That distinction between liquid outer core and solid inner core isn't just a geological detail. It's the reason Earth has a magnetic field at all. Earth's magnetic field is produced by what's called the geodynamo. As the planet loses heat from its interior, liquid iron in the outer core moves in convective currents, hot material rising, cooler material sinking. Combined with Earth's rotation, those movements organize into complex, self-sustaining electrical currents that generate a magnetic field. Think of it this way: a spinning, conducting fluid, driven by heat and shaped by rotation, producing magnetism. Not a permanent magnet. There's no giant bar magnet buried at the core. It's a continuously generated, continuously maintained field. And that distinction matters, Because it means the field is not static. It changes. From inside the core, the field extends through the mantle and crust and out into space, often tens of thousands of kilometers above Earth's surface. That region is called the magnetosphere. It's asymmetric. On the sunward side, the solar wind, a continuous stream of charged particles flowing out from the sun, compresses the magnetosphere inward. The boundary, called the magnetopause, sits at roughly 60,000 to 80,000 kilometers from Earth on that side. On the night side, the solar wind stretches things out into a long tail, extending millions of kilometers into space. Now, that open question I mentioned earlier, the magnetic poles wander, and the entire field can reverse, north becoming south, south becoming north. This isn't speculation. The evidence is locked into ancient volcanic rocks. When lava cools and solidifies, iron-bearing minerals freeze in alignment with the field at that moment. Layers from different geological periods show clearly that it's happened many times. The most recent full reversal, the Brunhes-Matuyama reversal, occurred roughly 780,000 years ago. What actually happens during a reversal? The honest answer is we don't know with certainty, because no modern human civilization has been through one. What the geological record suggests is that the field weakens significantly during the transition, and may become more complex and multipolar before re-establishing in the opposite direction. Reversals appear to take somewhere between 1,000 and 10,000 years to complete, slow by human timescales, fast by geological ones. Whether this would be catastrophic for life is a genuine open question. Earth's atmosphere provides some radiation shielding, even without a strong magnetic field, and there's no clear mass extinction tied to known reversals in the fossil record. But our satellite infrastructure, power grids, and communications networks exist in a world that has always had a stable, strong magnetic field. A significantly weakened field would have implications for those systems worth taking seriously. To appreciate what Earth has, it helps to look at what its neighbors don't. Mars once had a magnetic field. The evidence is still there. Magnetized strips of ancient crust in the southern highlands, frozen evidence of a time when Mars had a functioning geodynamo. Subscribe so you do not miss it.